Thank you.
Welcome. So for number 9, we have a subspace H of R9, and its dimension is 2.
Mm-hmm.
And then we have its orthogonal complement, H perpendicular. And we are trying to find a true statement. Is the first one true?
Could be true.
No, can't be. Can never be true. If you have studied set theory, you should know what the word complement means. So if this is a set, let's say A, anything that is not inside A, anything that is not inside that set is the one that is called the complement of A.
Okay. So it's like the opposite.
Yeah. Yeah. It's the opposite.
Okay.
Yeah. So this cannot be true. H cannot be part of its complement because they are opposites. The dimension of H pop cannot be 2 because you see the dimension of the whole space is 9. So it means that the dimension for H pop has to be 7.
Okay.
Yeah. And then the dimension of H plus the dimension of H pop can never be 4. It's going to be the whole space, 9. Okay. And then this one is true. Because if you have a vector space, let's use an example in the axis.
Yes, I remember you told me that.
Yeah.
The perpendicular is
the
y-axis.
Yeah, and they only meet at the origin.
Yeah.
The 0 vector. And so that's our answer. The fourth choice.
Okay. Should I check the answer?
All right.
So yes, it's correct. Number 9. Yes.
Yeah. Okay. So we go to 10. Which of the following matrices is orthogonal? Remember last time I taught you how to check whether matrices are orthogonal? You just multiply them and see if you're going to get 0 for your answer. And you can see clearly this one is orthogonal. Because 2 times 0 plus 0 times a half is 0, right?
Yes.
Let's look at this. This is 1 times -1 plus 1 times 1. It's 0, right?
Yes.
And then we have 1 times 1.
This one is wrong.
So it's going to be
A and B.
Yeah, so it's going to be A and B. So there we use the dot product. We usually say that the dot product of orthogonal vectors, is 0. Yeah.
I checked the answer and they say that it's only B. because each column of B is a vector of normal 1, and 2 columns are orthogonal. So the columns of B form an orthonormal basis.
That's not correct. Not unless they wanted to ask whether it's orthonormal. You know, the question didn't ask whether it's orthonormal.
Yeah.
If the question was asking for orthonormal, then we would have gone with B. But talking about orthogonal, A is indeed orthogonal. You see my argument?
Yes,
yeah.
I understand. But it's weird that they say that it needs to be orthonormal for basis R2.
Okay, let me just confirm the definition for orthogonal then. No, there is no need for confirming, but let me confirm. Orthogonal.
Yeah, because I know that the orthogonal is when it's 90 degrees to each other. So when you multiply the two vectors equals 0.
Actually,
and when it's orthonormal, the length is 1.
Yeah, the length is 1. Actually, can you just have a look at this? This is 2, 0, right? It's going to be that vector, right?
Yes.
And then look at 0, 1/2. That vector. Aren't they meeting at 90?
Yeah.
So maybe they just wanted us to look for orthonormal. Maybe the question was wrong or the marking scheme was wrong, but most probably the question was wrong. It should be orthonormal.
So if they ask for orthonormal.
If they asked for orthonormal, the normal means that the two vectors have to be orthogonal and they must have length 1 and of length equals 1, like that.
Yeah, okay. So B has the length 1.
Yeah, so
it's orthogonal.
Yeah. So B is orthonormal. A is orthogonal. And then C is none of the above.
I need to write this down. That he got it wrong. Which question was it?
Question 10.
10, okay.
Yeah.
10. Okay. Then move on to the next one we should. So question 11. Consider the following line L, subspace R3 in plane, given by parametric equation.
Okay. Do you think they are parallel?
I have no idea. Should we, how do you need to do it? Should we put like t as a number, for example 2, and r and s as 2 also, or
so let's see. Let's put t as a number. Can we use 1? So this would be 2, right?
Yes.
And then can we use r for 2? So when t is 1, xyz becomes 2. Minus 1 plus 1 is 0.
Yes.
Minus 1 plus 2 is 1.
And
then when t is 2, 5 becomes 2.
They have a s too, so.
Oh, they have s.
Yeah.
So let's see. Let's make s equal to 1. So that we can have 2 and 1. If this is going to be a 0, then we can conclude they are parallel.
Yeah.
So this is going to be 4.
4 plus 3 minus 6.
Minus 6, which is 1. And so they are not parallel. Yeah. Not parallel. Okay.
So,
if L was a subset of pi, then they had to be parallel. So the fact that they are not parallel also means that L is not a subset of pi.
so L and pi are, I don't think they're perpendicular.
They are not perpendicular either, because if you multiply like this two, you don't get 0.
Yeah, I think it's L and pi intersect.
Yeah, they intersect,
but they're not perpendicular.
Yeah.
Because they have, they just change the value y.
Yeah.
Should we check the answer?
Let's, before we check the answer, can we, maybe we can, let's see. Intersecting means that we can find a vector.
Yes.
That can give us a common, so we can set t plus 1 equals r.
Yes.
And then negative t plus 2 equal s, right?
Yes. Then, yeah.
So this would be x equals t plus 1, and then z equals negative t plus 2, and then y would be equal to 2
t plus 1
t plus 1
plus 3 times
negative
minus
t plus 2 minus 6. So y would equal 2t plus 2 minus 3t plus 6 minus 6. Those two cancel. So y equals
minus t
minus t plus 2. Oh, y equals minus t plus 2. So, okay, minus t plus 2. So the only time
yes.
Are they intersecting?
But isn't, we decided the value of R and S. But
yes.
If we change the value, for example,
okay.
if you do.
So x equals t plus 1. What do you suggest? Y equals minus t plus 2. And then z equals minus t plus 2. So what makes this negative t plus 1 equal to negative t plus 2? Nothing. Nothing makes these two equal.
Mm-hmm.
So there is no common point for the two lines. They don't intersect. This one is confusing because the fact that they don't intersect would mean that they are parallel to each other.
But how do you know if they are parallel?
Because they don't intersect. How do you define parallel lines?
Yes.
How do you define parallel lines in basic geometry?
Two lines with the same gradient.
Yes, two lines with the same gradient. Do they meet?
No.
So you see, if two lines are not meeting, what does that tell you?
That, yeah, they are parallel.
Yeah, so what happens when they meet? If they meet, they are not parallel. If they don't meet, they are parallel. So the fact that I couldn't find a T where such that the two lines meet, right? This meant that they cannot be perpendicular because perpendicular lines have to meet. They cannot be this one because we didn't find a point. So I go with L and pi are parallel, but I got 80% confidence. So can you check?
Yeah, it says L and pi are parallel.
Yeah.
The direction subspace of L and pi are HL equals span 1 minus 1 minus 1, and H pi equals span 1 2 0 0 3 1. Since 1 minus 1 minus 1 equals 1 2 0 minus 0 3 1, we see that HL is a subspace of subset of H pi, and L is either contained in or parallel to pi. To distinguish between the two, it suffices to test one point of L, for example, 1, 1, 2. From R equals 1, S equals 2, we find 2R plus 36 minus 6 equals 2, not 1. So the point is not in pi.
What a long explanation.
So they calculated the span, which is 1 minus 1 minus 1. And 1 2 0 0 3 1. Okay.
So the span of L was 1 minus 1 minus 1.
Yes.
And then the span of pi was 1
1 2 0
2 0
0 3 1.
0 3 1. And then how did they use that to?
And they found out that 1 2 0 minus 0 3 1 equals 1 minus 1 minus 1.
1 minus 1 minus 1.
so they are parallel.
Okay.
So it doesn't mean that when the span okay, so when the span times scalar. Okay, so when the span times when the scalar times the span equals the span of the other plane.
Yeah.
Then doesn't mean they are parallel. Is it always correct like that?
Actually, I feel like it means that L is going to be contained inside pi. That is what I got from this, because you see, it's like we took the basis of pi and then we produced the basis of L, meaning that the basis of L is inside, can be generated using this, right?
Mm-hmm.
I feel like whatever they showed is showing that L is contained in pi, according to all this explanation.
Yeah, but after they said that if you put values for t as we did before,
yeah,
at the end y of the pi of y is +1, then the y of L.
Yeah.
So at the end it's not inside, is it? Yeah.
It's not inside pi. Yeah. Okay, so my argument was simple. I just checked number 3. I just checked number 3, whether the two planes intersect, you know. If they intersect at some point, at some line, let's say this point, that is the only time. If they intersect, they cannot be parallel, and this one fails, but it could be this one or this one, right?
Mm-hmm.
So first of all, I found they are not perpendicular because I multiplied 2 vectors and I didn't get 0, right?
Mm-hmm.
And then I found that they cannot intersect. Because they cannot intersect and they are not perpendicular, it only means that they are parallel.
Okay.
Yeah.
Oh, this is conics.
Yeah.
So let's see the subset described by an equation of the form. Yes. So it has one positive and one negative, which means that I have a paper with all the equations of the conics. So if there's one positive and one negative, then it is a hyperbola. So it should be the second one.
How do you know?
So my teacher gave me, or gave to everyone, a paper that has all the information, all the equation of conics and quadrics.
Can you share that paper with me? Is it hard copy or soft copy?
I have a paper, so I can take a picture and send it to you.
Yes, of course you can. And just take a picture and send. I'll appreciate.
I just send you the conics one.
Yeah.
And yeah, so this paper he said that he's gonna give it to us during the exam. So normally it should be fine.
Oh.
It's weird that if he's gonna give us the paper, he will. I don't think he will give us a question with the answers already. It's kind of easy. It didn't need any calculations.
Yeah.
I understand. So I don't know. It's very, or maybe he won't give it to me during the exam. I don't know. He said he will.
If he said he will, I know he will. He's going to. They never lie.
I hope so. Or maybe I misunderstood something, maybe. I'm not sure about it.
Okay.
Did you receive it? I sent it on the reply message.
Let's see. Okay. I can see you sent it, but when I click on it, it doesn't open. Let me try with my phone and see.
May I go to the bathroom very quickly?
Yeah, sure. So my phone is downloading.
Okay.
Yeah, I've received it. I have it.
Okay, I'm back.
Welcome back.
Thank you. Okay, so let's start the open response question.
Okay.
Grassman's.
Ever heard of it?
Yes, I think so. But I don't remember. What's the Grassman?
Okay.
Do you know what's Grassmann's formula?
No. But it has everything to do with vector spaces.
Yes, normally,
Yeah.
yes.
So let us skip number 1. So I will just look into Grassmann's formula, and then I know I'm going to understand it. It must be simple, and then we are going to come back to question 1.
Okay. Then question, so should we go to question 2?
Yes, we can go to question 2.
Okay.
Yeah. Yesterday I slept at 4 in the night, and then the baby woke me up. The baby woke me up at 6.
So you don't have much sleep.
Yeah. So I thought, and then I tried to sleep during the day. I had to meet some students and do something. And then right now I feel like falling down. So when I saw Grassmann's formula, I was like, oh no, I'm not touching it. Okay, so number 2, we have L, V to W is a linear map. What is the relation between the dimensions of the vector spaces? Kernel of L, image of L, V, and W. Kernel of L. So let me try to visualize it. So first of all, the kernel of L is going to be, so this is V, and then this is W, and then L is mapping elements from V to W, right?
Mm-hmm.
And then the kernel of L is going to be contained inside V. It's going to be in there. This is the kernel of L. And what will happen about all these elements in the kernel? They are going to be mapped to 0. All these elements, they're going to be mapped to 0 in W. And then the image of L is going to be all the other elements that are not in the kernel. So every other element that is not in the kernel, it's going to be taken inside W, and it's going to occupy some space. And so this is the image of L. So what is the relationship between the dimensions of the vector spaces, the kernel of L, and the image of L? So V and W, let's see. What I know is that if I take the dimension of the kernel, and then I add to the dimension of the image of F, this should give me the dimension of V. That should give me the dimension of V.
Yes.
So that is one relationship. But okay, is there any other relationship? Just check your answer. I'm only finding this relationship.
What about V and W?
Oh, V and W, the relationship between V and W?
Yeah. Okay, so the answer says the relationship is dimension image plus dimension kernel equals dimension V by rank nullity theorem. And
so whatever I've written is in the answer, right? What else?
Yes.
What else have they written? You know, the question was open-ended. I was like, what else should I say?
And I think after is about the second question.
Oh, so this was it for the first question, right? Oh,
yes.
Okay. Yeah, because I was like, what else can I say? I couldn't find anything else to say. So this was an application of rank nullity theorem.
Mm-hmm.
By the way, how is the COVID situation in your country?
It's getting worse.
Oh,
but it's getting, the cases are increasing a lot.
And the deaths?
Death, not that much.
Or because of the vaccine, right?
Yes, yes, and there's more hospital, like there's more space, there's more cure, and they know that how to react against the virus. So
okay.
yeah, there is very few deaths, very small.
I'm happy to hear that. My grandmother, I think my grandmother has COVID. She is in isolation right now, and she's old. So when you're telling me that people are not dying, I'm like, oh, he's not going to die. Yeah. Okay.
How old is she?
She is 76.
Oh, okay.
Yeah. Don't tell me that she's too old that she's going to die.
No, she's quite. My grandpa is 80.
Oh, okay. Still alive.
And he got the virus, and he's still alive.
Oh, nice. Actually, I'll call my grandma and then I'll tell her about your grandpa, and then she will be okay. Yeah. So your grandpa was vaccinated?
Yeah, she was. He was, yeah.
Oh, nice. Even my grandma is vaccinated, meaning that maybe she's going to make it.
Yes.
All right.
Let's hope so.
Okay, so we go to part 2.
Yeah. Consider the linear map L R3 equals to RT defined by L A B C equals A minus B T cubed plus B minus C T squared plus A minus C T. Find the basis of image L. So the basis, how do you find the basis of image L? Wouldn't be the normal basis of the linear map?
So to find the basis, you will just take the basis of R3, right?
Yes.
And then look at its map, how it's going to behave. For example, what is L of 1, 0, 0?
Then
1 minus 0. So it's T cubic.
T cubic. Then B minus 0 minus 0 is 0. A minus 0 is 1.
0 minus 0 is 0.
Plus T. T cubed plus D.
So T cubed plus T. So that is one basis. another basis, L010, it's going to be A minus B, negative.
Minus 1, negative t squared, t cubed.
T cubic, B minus C.
Plus t squared and 0.
So T squared minus T cubic. And then L of 001.
It's going to be minus t cubed square minus t square.
Minus T squared.
Minus t.
Minus T squared minus T. Minus T squared. Minus T. Okay. Find a basis for that. So this is my thinking. That's going to be the basis. We could factor out t, but can we factor out t? Let's see. This could be t squared plus 1. And then t minus t squared. And then minus t minus 1. And then we have t on the outside. And then can we check for linear independence or dependence? Is there any? I don't think so.
Yeah, I don't think so.
Okay. Can you?
Yes.
So this is 50% confidence level.
But could you? We want the basis of the image.
Yeah.
And we just found the basis of linear map L.
We found the basis of the image.
Why would it be the image?
Because you see, this is the basis. L is taking a basis to a basis. So it took this basis. This is the image of this basis, right?
Mm-hmm.
This is the image of this basis. This is the image of this basis. And the other one was the image of the other basis. This is the image of this basis. So the three of them form the image, the basis of the image of L.
Okay.
Yeah. Just check your answer, because like I told you, I'm 50% confident in number 2.
The subspace image L is span LE1, LE2, LE3.
I'm right. I'm so happy.
Span t cubed plus t minus t cubed plus t squared minus t squared minus t.
Yeah.
It is clear that t cubed plus t minus t cubed plus t squared are linear independent.
And why was I 50% confident? I'm pushing it to 100.
Whereas minus t squared minus t equals minus t cubed minus t minus minus times minus t cubed plus t squared.
So they're checking for linear independence there.
Yes. So the last minus t minus 1 is linearly dependent.
Good. All right. So we have 100% for question 2.
Yeah, but we had to take off minus t minus 1. So
wait, why did we take off minus t minus 1?
Because it's linear dependent.
Wait, is this not the answer?
The answer is only t cubed plus t and minus t cubed plus t squared.
Oh, because this one is going to be, there is going to be some sort, yeah, I see it. If you take t cubed minus, if you take t cubed plus t, you add to negative t cubed plus t squared. The two cancel, you get t squared plus t, which could be multiplied by -1 to get you to that. Okay. So yeah, linear independence was scrapping that out.
Could we verify using the equation of linear independence?
Yes, we can.
Which is, for example, scalar times vector 1 plus scalar 2 times vector 2 plus scalar 3 times vector 3 equals 0.
Yeah.
And every scalar should equal 0.
Yeah. T cubed plus t squared minus t cubed. Negative t squared minus t equals 0. So this is lambda 1 t cubed plus lambda 1 t plus lambda 2 t squared minus lambda 2 t cubed plus, minus lambda 3 t squared minus lambda 3 t equals 0. So lambda 1 minus lambda 2 t cubed, and then lambda 1 t, lambda 3 t, so plus lambda 1 minus lambda 3 t plus lambda 2 t squared, lambda 2 minus lambda 3 t squared minus lambda 3 t squared equals 0.
How do you verify? How do you know? Yeah.
Okay. We need to show that one of them could fail to be 0, right? So what if lambda 1 equals lambda 2 equals lambda 3? What would happen if all of them are equal?
And then lambda 1 minus lambda 2 equals 0.
So we could just pick a number. Pick 3, 3, 3, 3, 3, 3. None of them are zeros, and we got a result of 0, so not linearly independent.
Okay, right. And then how do you know which one is not independent?
How you know which one is not independent?
Yeah.
So now, so the only way to know which one is not independent is to use linear combinations. Okay. And by linear combinations, I mean, we could go back to this. So let's see, which one could we write as a linear combination of the other? You see, we have given a condition that if all these lambdas were equal, then we would get 0, right? Okay.
Yeah, I'm a bit confused.
Where is the confusion?
Because I don't really understand how, because we have 3 bases.
Yeah.
And how do you know which one is independent and which one is not? Because they have t. It's it's like, it's not a number. It's not fixed.
Why don't you factor to know which one is independent? You could factor. For example, so my basis was, let me write my basis all over again. So this was t cubic plus t. I could say t squared plus t, right?
Mm-hmm.
And then I could write this as t, and then t minus t squared.
Yes.
And then the last one, I could write it as minus t, and then t squared.
T minus 1.
Minus
T plus 1.
T plus 1.
Yes.
Okay. So that's minus t.
The first one should be, sorry, the first one should be t times t squared minus plus 1.
Yeah, plus 1. Oh, now you've seen your dependence come in. No, not yet. T squared plus 1, t minus t squared. Okay. Now, look at this one. What if instead of factoring minus t, what if we factor out minus 1? Minus 1.
So t squared plus t.
T squared plus t. Okay. So in short, what I'm trying to say is that there is no unique way of checking the guy that's going to be dependent. You have to do your linear combinations. You have to check whether there is a way you could combine your vectors, 2 vectors to get 1 vector. Because whatever I was trying to do using factoring, I wanted to see if we can find 1 vector that is a scalar multiple of the other, and we didn't, right? So no vector is a scalar multiple of the other, okay? So now what we do, we try combinations. Why don't you take the first 2 vectors? T cubic plus t, and then you have some scalar, and then you add to the second one, t squared minus t cubic. And then try fixing some scalars that can give you the third one. If you do 1 and 1, this is going to be t plus t squared, right?
Yes.
Actually, you could do -1 for this scalar and -1 for this scalar to get -t minus t squared. And so you see -t minus t squared is a scalar multiple of the other. So there is no like a fixed way of doing it. It's sort of trying.
Okay.
Yeah.
But so when you add two vectors together and equals another vector, does it mean that the two vectors added together are linear independent, but not the one not added, like the last
the
one?
vector they produced cannot be part of the basis. Actually, I strongly feel we could just pick any two.
It doesn't mean like, so it's a bit random because we chose the first two.
Yeah, and the answer is not unique.
Using the scalar, it becomes the third one. So now we know that the first two are independent. But if I chose the last two,
so this is the answer we got, right?
Yeah.
Now let's do what you're saying. We are going to get a different answer, and it's going to be acceptable.
Is it the same? Because yeah,
it's going to be a different answer because bases, they are not unique. What if we pick T3 plus T and some scalar plus some other scalar, negative T squared minus T, right? So why don't you let this be 1 and then let this be 1? What are you going to get? T cubic, T minus T 0. So you're going to get T cubic minus T squared. To get T cubic minus T squared. So which ones did I took? I took T cubic plus T, and then I took negative T squared minus T. You see what I got? T cubic minus T squared, right?
Yes.
Which is, if we could negate it with a negative 1, this is T squared minus T cubic. And so we can kick that out and say that our answer is T cubic plus T negative T squared minus T. So in short, you just pick any two, and this is going to be an acceptable answer as well, because basis is not unique.
Okay.
Yeah.
Okay, so let's do 3. Give the definition of orthonormal basis of a subspace.
Yeah, so can you give that definition?
Yeah, so orthonormal basis, it's when the length of the basis equals 1, and it is orthogonal also. Orthogonal, which is when multiplying two vectors, basis vector equals 0, which means they are perpendicular to each other.
Yeah.
This one?
Yeah, that's right.
But if I write what I said, even though it's not the best language or vocabulary, is it correct? Because I didn't write any math, because I know that if I look at the answer.
Okay, so let me try to write.
There are many, like, B1 goes to BD of H such that the length of BI equals 1 for every I, and BI times BJ equals 0 for every I not, which is not equal to J. So it is very, like, yeah, it is.
So you like see this step?
When I speak, I don't say that. I just say what I said. And do you think it's correct?
Without using any math?
Yes, like the way I said. And I write the way I said.
If I was your teacher, and the question is 4 marks, I would give you 3.
Okay.
You would lose like a very tiny bit.
Mm-hmm.
So what you need to say that B1, B2, B3, Bn is an orthonormal basis of H Rn if B1 B2. So I want to say linearly independent. So if alpha B1, alpha 1 B1 plus alpha 2 B2 plus alpha n Bn equals 0, if and only if alpha I equals 0 for I running from 1 to n, for I running from 1 to n. So this is
but now
linearly
you're saying the
independent.
definition of linear independent.
Yeah.
But wouldn't like also no more basis always be linear independent? But in the answer, they didn't write anything about linear independence.
Okay, so this is what I'm trying to write my answer and then we compare with their answer.
Okay.
So first of all, I have to say that the basis elements are linearly independent. And okay, so they are linearly, okay, mine is quite long because right now I'm insisting it's a basis, linearly independent, and H equals span B1, B2 up to Bn. So that's a basis. So up to this point, I am just saying that this set is a basis of H. And then, and that further, Bn, Bi, their length has to be equal to 1 for every I. Their length has to be 1, and Bi multiplied by Bj, the dot product between Bi and Bj, is 0 for I not equal to j. So maybe your book is going to ignore this part because already it's assuming it's a basis. It's assuming it's a basis. And then you can say that B1, B2 is another normal basis if the length of each element is 1 and the dot product is 0 for I not equal to j.
Okay.
Yeah. So you usually don't lose marks for talking too much. Because you see here, I talked too much, right? You'll never lose marks if you talk too much.
Yeah.
But you can lose marks if you talk.
Yeah, I could lose point if I talk less.
If you talk less, you're going to lose marks.
But if I talk too much and it's wrong,
again, if you talk too much and it's wrong, you lose marks. So you should, if you're not so sure, don't talk too much.
Yes.
But if you are sure of what you're doing, you are allowed to talk too much. So how do we come up with an orthonormal basis of R3 consisting of eigenvectors of this matrix?
So you so you divide its length. You divide it by its length.
No,
so
you have to find eigenvalues.
would they say that find an orthonormal basis of R3 consisting of eigenvectors of the matrix? Ah, okay. I thought it was I thought A was the eigenvectors. Okay, so no, we need to find the eigenvalues and eigenvectors, then make the eigenvectors as orthonormal basis.
Yeah.
Correct?
Yep. So A minus lambda I is 1 minus lambda 1 1 1 1 minus lambda 1 1 0 no 1 1 1 minus lambda.
But could we simplify? Oh no, we could not. Well, is it no? But wouldn't be if I reduce it to Roshan form, wouldn't be equal to 1 1 1 then O 0?
It would
if I minus the first row with the other row.
If you reduce it to echelon form, you're going to get 1 alpha 1 equals 1, alpha 2 equals 0, alpha 3 equals 0.
Yeah.
But yesterday when we looked at reducing a matrix in row echelon form, I think we observed that some properties usually get lost, right?
I know that was when we did, what was it? No, that's when we did the determinants equals the pivots.
Yeah.
The multiplication of pivots. So in this case, it would equal to 0 because if I do row echelon form, it would be 1 1 1 then O 0. So it would be 1 times 0 times 0. And it would equal 0. That was the yesterday argument. But I think if you reduce to echelon form and then use the equation to find the eigenvalues, maybe it will work. But we could try. Yeah.
Okay. So let's test this then. Let's see if we are going to get 1 0 0. So this is 1 minus lambda 1 1 1 1 1 1 1 1, and then you have minus 1 and then 1 1 1 1 minus lambda 1 1 1 1 minus lambda, and then plus 1 1 1 minus lambda 1 1. This is 0.
Wait, wouldn't be that? No, the first one, it wouldn't be 1 minus lambda, then determinant of 1 minus lambda.
Oh, yeah.
1 minus lambda.
1 minus lambda 1 1 1 minus lambda. Yeah. And so this is 1 minus lambda 1 minus lambda squared minus 1, right? And then this is minus 1 1 minus lambda minus 1, right? And then this is plus 1 1 minus 1 minus lambda. equals 0. So 1 minus lambda cubic minus 1. This is minus 1 plus lambda plus 1. So this is minus 1, and this is just lambda plus lambda, right?
Yes.
And then this is 1 minus 1 plus lambda. So this is plus lambda equals 0.
Mm-hmm. So it is
1 minus lambda cubic
plus 2 lambda minus 1 equals 0.
plus 2 lambda minus 1 equals 0. It's going to be a cubic, right? Can we be lazy and just get the lambdas using because once I saw this trinomial function,
Mm-hmm.
I really don't like it.
But how would you do it?
So let's open it. 1 minus 3 lambda minus 3 lambda plus 3 lambda squared minus lambda cubic plus 2 lambda minus 1 equals 0.
Wait, so is there like an equation for cubic? For example, 1 minus lambda cubic equals.
Yes, I used the Pascal's triangle. It's called binomial theorem.
Okay.
Yeah.
Could you write it down, please?
So usually if you have A plus B cubic, this is A cubic plus 3 A squared B plus 3 AB squared plus B cubic. So in this case, I had 1 plus negative lambda cubic. So this became 1 cubic plus 3, 1 squared negative lambda plus 3, 1 negative lambda squared plus negative lambda cubic. So this became 1 minus 3 lambda plus 3 lambda squared minus lambda cubic. That's how I got this.
Okay. And for A minus B cubic.
You see what I did? I used, so we usually use this, but now we, instead of B, you replace B with negative B, right? Yeah.
So it becomes A cubed minus 3A squared B.
Yeah.
Minus 3AB cubed.
Plus 3AB squared.
Oh, yes. Okay. And minus B cubed.
Yeah. Okay. So this would be negative lambda cubic plus 3 lambda squared minus lambda. And then the ones cancel.
Yes.
Equals 0. So this is lambda. And then, so let's do negative lambda so that this becomes lambda squared. Lambda squared plus 3 lambda minus 1 equals 0. So 1 lambda is going to be 0.
Yeah.
And then the other lambda is going to be lambda equals negative 3 plus or minus square root of 9 plus 4 over 2. So it's going to be, the other lambda is going to be -3 plus the square root of 13 divided by 2, and the other one is -3 minus the square root of 13 divided by 2. I don't know. I'm not trusting my brains today. Let's confirm it. So eigenvalues of, it was 1, 1, 1, 1. It was 1, 1, 1, 1, 1, 1, 1. Go.
What does it say?
Oh, you cannot. It's giving us
No,
2 zeros
yeah.
and a 3.
Yeah, I look at the answer, they say, we immediately see that rank A equals 1. So dimension no A equals 3 minus 1 equals 2. And lambda equals 0 is an eigenvalue of A with geometric multiplicity of 2.
Yeah.
The eigenspace is E0 equals no A equals span 1 minus 1, 0, and 0, 1 minus 1. We also notice that A 1, 1, 1 equals 3, 3, 3. So lambda equals 3 is an eigenvalue of A necessarily with G3 equals 1.
So they didn't use any of the methods.
No, I don't know how they come up with that.
No, we should have gotten it as well.
And we did a mistake somewhere.
Maybe we missed it somewhere, but we should have gotten it. Let's see. We should have gotten it as well. Because so our problem is just somewhere in the calculation. Yeah. Just a sec.
But how do they find out without doing any calculations? So do you think there's like a method to find quickly the eigenvector, eigenvalue? Because when I do like those exercises, I spend so much time on just finding the eigenvectors and eigenvalue.
So they said the rank of the matrix is 1, right?
Yes.
So I think we can conclude that if the rank of your matrix is K and the dimension is maybe N, and that rank K is less than N, then lambda equals 0 is an eigenvalue with multiplicity N minus with multiplicity N minus K.
n minus k. For example, in this case, we have rank equals 1 and dimension equals 3.
Yeah, so 0 is going to be an eigenvalue of multiplicity 2.
But is the phrase, the definition you just wrote, is it like, is it something like for every vector, for every matrix?
I want to believe so.
Okay, could we try for another vector, another matrix?
Yeah, let's try. Let's see. Can we have, let's use, can we do 4 by 4?
Yeah. Oh, could you go back so I can write the sentence you just wrote?
Okay.
Please, thank you. Okay.
All right. So let's try 4 by 4. Let's have 1, 2, 3, 4. Oh, this is not 4 by 4.
Oh, I cannot see what you're doing.
Oh, you can't?
Yeah, I cannot.
How about now? Can you see?
It just, oh yes, now yeah.
Okay. So let's see. 2, 4, 6, 8. Two, 4, 6, 8, 4, 9, 2, 1. Oh, 4, 9, 2, 1, 3, 6, 9, 2. What is the rank of this matrix?
I would say 3.
I'd say 2. Rank equals 2. Dimension equals 4.
Mm-hmm.
So 4 minus 2 equals 2. So I expect alpha 1 to be 0. And I also expect another one to be 0. And I don't really know much about the other. Let's see if it's right. You know, we're just trying to prove our conjecture. You see? We are right.
0 with multiplicity of 2.
Yeah.
But how do you know the rank was 2?
The rank was 2 because there were only 2 linearly independent.
Oh, I see.
Yeah.
Because the first row and the last row is just times 3.
Yeah.
I didn't see that.
So at least you have seen one way of finding if we have a 0 in our eigenvalues as our eigenvalue.
Okay.
Yeah.
And okay, so we know that there's 0 and we just need to calculate 3
Yes.
3, the other one.
Yeah.
But how, again, the answer, they don't show any calculation. They just wrote the eigenspace is E0 equals null A equals span 1 minus 1, 0, 0, 1, minus 1.
Okay.
We also notice that A 1, 1, 1 equals 3, 3, 3. So eigenvalue is 3. Like how, I don't understand how they found, I don't understand how they found out that the second or the third eigenvalue is 3 without doing any calculation.
Okay. I'm also trying to figure that out, like how they got 3 without.
Like how they found the span 1 minus 1, 0 and 0, 1 minus 1.
Can we try calculating it to see if our knowledge that one of the lambdas is 0 is going to help us?
Mm-hmm.
So this is 1 minus lambda, right? And then 1 minus lambda squared minus 1, right?
Mm-hmm.
And then minus 1, 1 minus lambda, minus 1. And then plus 1. Please check whether I'm making any mistakes.
Mm-hmm.
1 minus
Yeah.
1 minus lambda equals 0. So this is 1 minus lambda, 1 minus lambda cubic minus 1 minus lambda minus 1
Mm-hmm. So you missed out the minus 1, the first minus 1.
Richard? This one?
Yeah.
Oh, not yet, Mister. I did this times this, give me this. And then this times minus 1, give me that.
Okay.
And then this is negative lambda, right?
Yes.
And so this is going to be plus lambda.
Mm-hmm.
And then this is 1 minus 1. This is negative lambda. And so this is minus lambda. And this is 0, right?
Mm-hmm.
So the 2 cancel. And then we get 1 minus lambda cubic minus 1 minus lambda. Or maybe we could say minus 1 plus lambda equals 0.
Wait, I'm sorry. For the last part, when we have 1 times 1 minus 1 minus lambda, the last part, and we find out minus lambda.
Should be plus lambda.
Isn't it minus 1 plus lambda?
this is 1 minus 1 plus lambda. So they cancel. So this is plus lambda. And so we have plus 2 lambda. It's taking us to the equation we had.
Yes. Plus lambda, yeah.
Like that.
Wait, why is it 2? Oh, yes, okay. Okay. So it is 1 minus lambda cubed plus 3 lambda minus 1.
And 1 equals 0. If we open up this, becomes 1 cubed minus 3 lambda plus 3 lambda squared minus lambda cubed plus 3 lambda minus 1 equals 0. These two cancel. And these two cancel. So we get lambda squared equals 3 minus lambda equals 0. So lambda squared equals 0. This means that lambda 1 is 0, lambda 2 is 0, and then 3 minus lambda equals 0 means that lambda equals 3.
Lambda 3 is 3, yeah. Oh, but what would... So last time we did something wrong.
Yes, there was a mistake. You see them, that's what I was telling you. Please check my mark. Yeah.
So now we have 0, 0, 3.
Yeah.
And then we need to find the eigenvectors.
Yeah.
Which would be so
eigenvectors associated with 0.
Yeah, it would be 1 wait.
So this is eigenvectors associated with 0, 1, 1, 1, 1, 1, 1, 1, 1, 1. So x plus y plus z equals 0. This could only be, let's say x is 1, y could be negative a half. So we could say 2, negative 1, negative 1. There you go. That's one eigenvector.
And there's 2 of them.
It's not unique.
And then for lambda 3, we will have -2.
-2, 1, 1, 1, -2, 1, 1, 1, -2. So let's reduce it. Half, negative a half. No, not a half, but 1, negative a half, negative a half. And then 1 minus 1, 0. Negative 2 minus a half, negative 2.5. 1 minus a half is a half. Right?
There wouldn't be 1 minus a half. So it'd be 1 plus half.
1.5.
Yeah. And for the other one, it would be -2 plus 1/2. So it'd be
negative 1.5.
Yeah.
Okay. And then this is 1 minus 1, 0.
0.
1 minus a half. 1.5.
Mm-hmm.
And then minus 2.
Minus 2.
Minus.
Minus 1.5.
Negative 1.5. So I guess at this point we can already find a solution, because we can see x is equal to z. Y is equal to z.
Y equal to z.
Or maybe let's finish the reduction, because
No, because minus a half is not y equals z.
So x equals a half y plus a half z, right?
Yes.
And then from these two we can see y equals z, right?
Yeah. Yes.
So we could have a vector 1, 1.
Then a half plus a half is 1.
Let's see. Minus 2 times 1 is minus 2. 1 times 1 is 1. 1, 0. 1 minus 2, 1. Yeah, so this is the other vector. Okay. Shouldn't we get three vectors?
No, because there's 2, 0. There's lambda 1, 0, and lambda 2, 0.
And how can we come up with an orthonormal basis of R3? If we only have 2 vectors, then okay, so this is what we will do. We have 2 minus 1 and 1, 1, 1, right?
Yes.
We can cross them. We can cross the 2. So we have 2 minus 1 minus 1. So we have 2 minus 1 minus 1. We cross with 1, 1, 1. But let us normalize them first. So this is 1 squared plus 1 squared, 2, 2 plus 4, 6. So the square root of 6.
6, yeah.
So 1 over square root of 6, 2, negative 1, negative 1. And then we are crossing with 1 plus 1 plus 1, 3. So we are crossing with 1
squared
over square root
of 3.
3.
Yeah, and 1, 1, 1.
1, 1, 1. Like that.
So now we normalized
Mm-hmm.
the vectors, and we're doing cross product.
Yeah. So can we, yeah. And this is 1 over square root of 2 multiplied by the square root of 3. No, 1 over 6, 1 over square root of 6. All right. So let us not try to be simple. So this is I, J, K. Let me just do 2 minus 1 minus 1. Let me assume the others, 1, 1, 1. So it's going to be minus 1 minus minus 1. It's minus 2, right? You remember how to do cross product, right? Minus 1 minus minus 1 minus 2. And then 2 minus minus 1 is 3, so negative 3. And then 2 minus minus 1, 3. And then we take we do 1 over. This is 4 plus 9, 13. 13 plus 9, 22. So
I'm
a square root of 22.
a bit confused what.
Uh-huh.
I'm a bit confused what you're doing.
I'm doing cross. I took this vector, the 2 minus 1 minus 1 and 1, 1, 1, and then I'm doing cross product.
Yes.
You remember how to do cross product?
Yeah, you use the determinant.
Yeah.
Then you cross the product.
Yeah.
Yeah, then we got minus 2, minus 3, and 3.
Yeah. And so my orthonormal basis.
Wait, wouldn't be. So for the first one, we have minus 1 times 1, which is minus 1, minus minus 1. So would it be 0?
Yeah.
And for J, we have 2 times 1, which is 2, minus 1 times minus 1, which is minus 1. So it goes 3. It's plus 3.
But for J, we usually negate it.
Oh, yes, true. Then K, yes, 3. 3 is fine. So 0 minus 3 is 3. And how did you get 1 square root 22?
It was, I had the 0. So this one has to change as well. It's going to be 1 over square root of 18.
Well, 18, which is 6 times 3.
Yeah.
So you just multiplied.
No, I found
square root.
I found the length of this vector. This is negative 3 squared, that's 9. 3 squared, that's another 9, that's 18. So its length is the square root of 18.
Okay.
Yeah. And so my orthonormal basis is going to be 1 over square root 6, 2, negative 1, negative 1. And then I have 1 over square root 3, 1, 1, 1. And then I have 1 over square root 3 multiplied by square root 6. 0, negative 3, negative 3. I'm trying to see if there is something common that we can factor out. But I don't think so. Is there?
It's 0, negative 3, and 3.
Yeah. So what basis did they get? It's going to be, I hope it's going to be similar to, it could be slightly different, but it should be related.
So the final basis, orthonormal basis of eigenvectors of A is given by the vectors square roots 1/2 minus square roots 1/2, 0, then square roots of 1/6, square roots 1/6, and minus square root 2/3. Then square root 1/3, square root 1/3, and square root 1/3.
Wait, square root 1/2, square root negative square root 1/2, 0, square root 1/6, square root 1/6. Keep going.
Negative 2/3. So minus square root 2/3.
Okay. I am below 0. What is below 0?
Yes, negative square root 2 divided by 3.
Negative square root 2 divided by 3. And then this?
Then square root 1 divided by 3. And it's the same.
1 divided by 3. Like that?
Yes.
Okay, so let's see if we can produce this from what we have here. So this is 2/√6.
So we have the square root.
So that's 2/√6. I could write 2 as the square root of 4. Square root 4 over square root of 6, and that gives me square root 2/3. Okay. And then this is negative 1 over square root of 6, which is negative square root 1/6. So whatever we got is similar to the answer because the basis cannot be unique.
So we got the two last bases correct.
The two last bases correct?
Yeah, and the first one I don't know yet.
So this is negative square root of 9 divided by.
Yes, it's correct. So we got everything correct, but just it's in a different order.
Yeah.
For example, the first one, we got 0 in first, and they got 0 in last.
Oh yeah.
So is it like, does it change anything? Is it still correct, or would that be wrong?
It should be right. It should be right because it's never unique. So what we had was an orthonormal basis as well.
Then our 0 is at X and their 0 is at Z. But wouldn't that change the value, the basis?
Okay, let's look at what they did.
And they used Gram-Schmidt.
They used Gram-Schmidt orthogonalization process.
Yes.
You know, when we started, I wanted to use Graham-Smith, but when it said we should use eigenvectors of the matrix, I changed my mind.
I don't know, it's very weird because they asked for the orthonormal.
Yeah.
And the process we did is the way to find orthonormal because cross product. And what do they mean by consisting of eigenvectors? So that 1, 1, 1.
Okay, so our answer is right because you see it depends on how we did cross product. You see, we did 2, -1, -1, 1, 1, 1. If you did 1, 1, 1, and then 2, -1, -1, you would get a different answer, which would still be correct because we don't have like uniqueness.
Okay.
Yeah.
Do you think we could do like a recap of what we did for the last question? Recapitulative.
For part 3?
We had many information. Yes. My brain is a bit confused.
Okay. Maybe to reduce your confusion, right? Stick to Graham Smith. Because Graham Smith is fixed, is a fixed method, and it's quite easy. Because I also wanted to do Graham Smith when we started, but this part changed my mind.
But isn't Graham Schmidt to find the orthogonal?
Graham Smith is to find, it's to find orthogonal bases. Yeah. But now you can just normalize them before getting to your orthogonal basis.
Could we try?
Yes, we could.
Okay, so
we can normalize
vectors we got.
Did we get the same eigenvectors as the question? Did we? What eigenvectors did they find?
They don't say yet. Eigenspace span 1 - 1 0 0 1 - 1 ends 1 1 1. So they say we find B1 equals 1 over square root of.
I was thinking
now in my brain I have your technique and the answer.
I'm losing your voice.
Just technique at the same time. I just said I'm getting confused because I'm watching your explanation, your technique, and also watching the answers technique. So it's getting very confusing.
Okay.
So could we try the Graham-Schmidt algorithm?
Yes, we can. I was thinking we could maybe start with this question because I also need to I need to fix my mind on it. Can we start with it in the next hour, the next lesson? And then I can also see that this is the last question, number 3. So
we had number 1 also.
Yeah, we had number 1.
Number 1, we didn't do it.
Yeah, we didn't. Okay, so I was asking whether you have another paper.
Yes.
Okay, so you can send the other paper. And then we are going to do number 3. Number 1, we will do it in tomorrow's lesson. So we will do, yeah.
Yeah, Thursday. Tomorrow I can't.
Yeah, that's today's lesson. That's today's lesson. So we will do number 3 and the other paper that you sent. Okay.
Okay.
Yeah. So looking at this paper, I think we did a fairly good job. Apart from number 1 and maybe 50% for number 3.
Okay. Could you send me the recording of yesterday's and today's?
Let me send it now before you go. So for today's, I'll send tomorrow because it has to convert.
Yeah.
So let me send you yesterday's. So So yesterday was 20th.
Yes.
I believe this is the one. All right, so you're going to receive it once it's finished uploading.
So this one is yesterday's?
Yes.
Okay.